We present ThalNet. In this work, we introduce a biologically inspired sequence model in which modules communicate with each other. Rather than specifying the network structure for a task, our model automatically learns the connectivity that helps solve the task. In doing so, our model discovers hierarchical structure, skip connections known from ResNet, and novel connectivity patterns. Our model is inspired by the communication of brain areas in the neocortex. While the neocortex is often described as a hierarchy, its areas actually connect in complex ways, including side connections and feedback loops. These areas mainly communicate in two ways, through direct connections and via the thalamus. Our work is inspired by the thalamus, which is located in the center of the brain. We now explain our model ThalNet. In ThalNet, multiple neural modules share features via a routing center. Modules are typically implemented as recurrent neural networks. At every time step, modules send their features to the center, where they are concatenated. At the next time step, the modules can read from the center. In practice, ThalNet can process input in many more complex ways. Modules read from the center through static or dynamic reading mechanisms. Here, we see one module that sends its features to the center, where it gets concatenated with the features of the other modules. The center is then multiplied by a learned reading matrix to produce additional input at the next time step. In the dynamic case, the reading weights are computed as a function of the current module state. Let's have a look at what reading matrices ThalNet learns. Every row in these matrices contains the factors for a weighted average with a center, resulting in one element that the module reads. The center contains the features of the four modules left to right. From the light block in the top left, we can see that the first module mainly reads features produced by the second module. From the dark areas along diagonal, we can see that the modules attend less to their own features. From the reading matrices, we can construct connectivity diagrams. Overall, ThalNet learns to route information in a hierarchical way. It commonly learns skip connections, as known from ResNet. We also observe long feedback connections, which we believe might benefit future sequence models. On the right, we see that our attempt to parameterize dynamic reading using fewer parameters did not result in interpretable connectivity patterns. We evaluated the performance of ThalNet on 3 sequential tasks. We asked the model to classify handwritten digits, observing only one pixel row at a time. Our model outperforms the baseline with the same number of parameters. On the CIFAR-10 images, the baseline overfits, whereas ThalNet exhibits a smaller generalization gap. We observe a similar result on the text-A language modeling corpus. Our model slightly surpassed the baseline performance while using 12 million instead of 14 million parameters. In summary, we introduce a modular sequence model that outperforms stacked GRU networks. We assume that the modularity and information bottleneck at the center act as a regularizer to improve performance. The long feedback loops learned by ThalNet might inspire future sequence models. We believe that ThalNet also provides a promising starting point for multitask experiments and for online architecture search. For more details, please visit the project page and read our paper.